So now today I'll ask you to add the cyclic prefix and transmit it through a wireless channel, some LTAPs. Okay, I'll describe how the channel should be simulated, and then calculate the error rate. Okay, and at the same time you can take the probability of error for QPSK for a flat fading channel. Okay, we'll describe what it is, and also average it. So the theoretical curve should match the. Okay. How about others? There are some students who didn't make. How about you? Did you make progress? No. Yeah, just discuss with them and figure out how to do it. Okay. So you had. How did you figure out all the random variables you know how to generate? The bit stream. Rand greater than 0 gives you the bit stream. Rand int gives you zeros and ones. And that's all you need. Okay. And for the channel, to generate the channel, you use rand n complex Gaussian distribution. Rand
This
n.
was for a unity channel.
So next time around, I'll describe you. You have to do it in a Rayleigh fading channel. You can use rand n plus square root of minus 1 rand n. That gives you a complex number. Okay. You can set the variance of.
Noise also be generated.
Noise anyway you need a rand n, right?
Not rand n, we can just use rand for real part and j times rand for.
That's not correct. Rand n. Noise is Gaussian.
Gaussian size 1 by root 2.
Rand is a uniform distribution between 0 to 1. Rand n is a normal distribution. How did you match the theoretical result? You probably didn't. It matched. Strange. There should be some deviation. Show me the code later in the class. I'll be after 2. I'll be downstairs. Okay. So you can. In fact, any one of you can come over there, sit with me, and go through.
So are you here? When are you here?
No, I'll try to stay here most of after 10 and any day after 10 and after 2. Lunch is 1 to 2. Okay, I'll try to be here so that we can discuss it. How about others? They're not coming?
They will be coming maybe in another 2 minutes.
Okay, let's just wait. Okay, so what we have to do is this week we should complete the code with cyclic prefix and a fading channel. Okay, that shouldn't be too difficult, and you can do it for one OFDM symbol. That's okay, and put them in a loop. Okay, and what I want you to do is I'll give you a MATLAB code for a convolutional encoder and decoder. Okay, of an arbitrary coding rate. You integrate that code with your OFDM transmission and get the results with channel coding. Okay, I don't expect you to write an encoder and decoder. It's a bit too much for this short course. I'll give you the code, and you can go through the properties of the code from the book Pravakis. Right? There is a convolutional encoder decoder section. If you want, you can learn it by yourself. Okay? We're not going to discuss in the class. And you can simulate it and see what the performance is like. There is a reason why I want you to do it that we'll discuss shortly. Okay, in fact, you can see the performance of the. Are you recording already? Okay, fine. In fact, you can see the performance of the link, that is the bit error rate, as a function of the code rate. It changes dramatically because the diversity order you will get at different code rates is different. Okay? There is a trade-off between the diversity order and channel code rate. Okay, that we'll discuss today. Let's see. Okay, I think we'll get started because we don't want to delay this lecture anymore. Okay, so where were we? Last time we ended up with an OFDM signal yk represented as hk hk plus nk. Was it yk that we wrote last time? Check your notes.
No, there wasn't RK.
RK, okay. Well, let's be consistent, okay? We'll call it RK. Okay. So, this is what we ended up with at the OFDM receiver, after going into frequency domain using a DFT. Okay? And the range of k is n minus 1. Like I said before, not all n tones are loaded. What it means is that xk may be absent for some tones. That is the level of flexibility OFDM offers. So if it is absent, you don't have to demodulate. The receiver knows that. Okay? No confusion about it. Okay. Compared to the AWGN channel, additive white Gaussian noise channel, where the channel gain was unity, see, we use this word channel to denote both NK and HK sometimes. You should read it in the context. When I say additive white Gaussian noise channel, we refer to the presence of NK. And we also call this channel, this is the medium through which the signal passes through. Okay, this also is called channel. So you should read it in the context. Okay? HK is the channel caused by the multipath propagation, and we showed it to be the DFT of h of L to the power minus j 2 pi L k by n, L ranging from 0 to some index. What is it? We call it V or something? Whatever is the length of the channel. Okay. V was the original channel length, but here we would call it maybe L minus 1. That is the memory we said. Total is L minus 1 or L? Do you remember? Total channel length is L. Okay. Length of the channel is L. Okay. 0 to L minus 1. You can keep it to n minus 1 also, and then assume that some of the HLs are zeros. Okay? This is what the receiver observes, h of L, in time domain. And after taking the DFT, h of k is what the modulation symbol experiences. H of k is what modulation symbol experiences. Okay? But you can already see that if the channel is h of L is a single tap, h of k will be flat, right? And the gain would be the same for all subcarriers. What are the subcarriers? Here k 0 to n minus 1 are the subcarriers. But if h of L is an FIR channel where, let's say, you have two taps, then if you take the DFT, you can see that h of k changes smoothly over the subcarrier indices 0 to n minus 1. So the channel is correlated in frequency domain. Channel is always correlated in frequency domain. Why we talk about correlation? If these channel taps are modeled as random variables, this also becomes a random variable, and it is correlated in K. Okay. For the time being, we are not interested in the statistics of h of k, but rather we want to understand the behavior of the link from a very fundamental standpoint. Okay, what is the behavior of the link from a very fundamental standpoint? Okay, so one metric that we want to use is the mutual information that you can get for each subcarrier k. Okay, the mutual information for each subcarrier ik is equal to logarithm base 2 1 plus the signal to noise ratio for that subcarrier, which is h of k whole square divided by n naught, and you can also write it as x sigma x square, which is the variance of the symbol set xk, and this formulation holds this mutual information as long as xk is complex Gaussian. Xk has complex Gaussian distribution with zero mean and variance sigma x square. So xk is distributed as complex normal, zero mean, and variance sigma x square. But in the beginning of the lecture, we said that xk is restricted to a finite constellation like VPSK, QPSK, and so on and so forth. But this is the mutual information you get for a constellation with a continuous distribution, and we use finite size constellations to reach this mutual information. Okay, this is something you have seen, right? Capacity of a channel. Here I use the word mutual information because we are not allowing feedback from receiver to transmitter. So you can also give feedback from receiver to transmitter on the channel states and get the ultimate capacity, which is somewhat higher than what you could get. Okay, you can optimize the transmit power on different subcarriers depending on the channel gain, which we will not do right now. Okay, so you can sort of treat it as a capacity without feedback. This is for single tone. This is for a single subcarrier. You can also write the total mutual information. This is the mutual information for subcarrier. Okay, the total mutual information for all n subcarriers is equal to the sum of mutual informations of different subcarriers. Okay, and that is equal to logarithm base 2 1 plus what are the units for this mutual information? Bits for some unit, bits per symbol. Okay, bits per channel use or bits per symbol. In this case, one subcarrier is the channel use, bits per channel use. Okay, so the total mutual information that you would get is sum of logarithm of 1 plus hk square sigma x square by n. Okay. Okay. So now we'll get a bound on this expression, and that bound reveals something about the diversity order of the channel. Okay, we'll talk about diversity. We'll have not yet introduced the notion of diversity order, but once we get that bound, we'll define what is diversity order. Okay. So pictorially, the channel is something like this: H0, H1 up till HL minus 1. That's in time domain. Okay, the index L. And these H0, these HLs can be modeled as complex Gaussian random variables. Zero mean. Okay, and we'll introduce a model here where we'll assume that all the taps have equal average power. Just a model, okay? And it turns out to be a pretty good model. And the variance of each tap is 1 over L because we want to normalize per tap variance to be 1 over L so that the total power contained in the channel is unity. Okay? Total power contained in the channel is. And H of L are IID. They are statistically independent of each other. Okay. This is the channel model in time domain. Nevertheless, OFDM is going to work in frequency domain. Okay. So what we will do is, we'll get an upper bound on this expression. We'll get an upper bound on this expression. So what we will do is, we'll multiply this by n and divide this by n. And this part can be bounded as n multiplied by, we'll move the summation inside the logarithm. Okay. this can be done by using what is called Jensen's inequality. Have you encountered this before? Huh? Jensen's inequality. So you must have seen this in digital communications or some other place. Huh? Information theory. Okay. You use this quite a bit in information theory. Okay. But it is a very useful inequality. Well, first of all, we moved the summation inside the logarithm. So we have something like, n times logarithm of 1 plus a single SNR. Okay, a single SNR. And this SNR can be related to the SNR of the channel. Okay, what is the SNR of the channel? Okay, so let's take this and see how we can manipulate it. This is equal to applying Parseval's theorem. H of k is the DFT of H of L, and H of k absolute value square summed over n subcarriers is equal to, and divided normalized with n is equal to what? Is equal to HL absolute value square. This comes from Parseval's theorem. Okay. So we first apply the Jensen's inequality, then we invoke Parseval's theorem, and this portion can be written. Where should I write it? Okay. I of n is upper bounded by n times logarithm base to 1 time 1 plus h of L I don't know if that is visible. Hopefully it is. I will probably rewrite it. Okay. This is a very important representation. I mean, this bound is quite useful because it tells us something about the channel. Okay. If I take all the channel taps and if I square them and add them up, that is the energy contained in the channel, or power rather than. Okay. Rather power. And this term can be treated as, I would call this matched filter bound, which is known as MFB. It is called the matched filter bound for an ISI channel. Well, in time domain, the way you apply this matched filter bound is, if it is single carrier transmission, you send a single symbol and you measure the impulse. I mean, you collect copies of that symbol and come up with some sort of processing to arrive at this. Basically, it's an ISI free channel. Whereas in OFDM, to arrive at this matched filter bound, probably you don't do a single shot transmission. Rather, you send the same symbol xk on all the subcarriers, okay, and then you do a match filtering, add them up, and the equivalent SNR would be the match filter bound. Okay, of course, sending the same symbol on all subcarriers will reduce the data rate by factor 1 over n. I mean, that's very inefficient way of doing it. Then you may ask why we are interested in this metric. Well, this metric is very useful because if I can send xk, different xk on different subcarriers, and at the receiver, by some means, we get an equivalent SNR, something close to this, then that's a good thing. Why is that? This is sum of squares of individual fading taps. They all add up coherently, and if one of these taps fade, the other need not fade simultaneously. Therefore, we have what is called diversity protection of order L. See the point? These are all fading taps, right? What is the probability? What is the distribution of the envelope of any of these taps? Well, for H0 complex, for complex process it is Gaussian. For the envelope, it's Rayleigh. Have you studied that? Rayleigh distribution. If H0 is a complex Gaussian process, the envelope, that is magnitude of H0, has Rayleigh distribution. Okay? Envelope of HL is square root of real part of H of L square plus imaginary part of H of L square, and for this random variable R, if you work out the PDF, the probability density function, it turns out to be Rayleigh density. Have you studied this in wireless? Okay. The Rayleigh random variable, the envelope, it goes through deep fades. Right? You send a symbol, you send, this has probably some 1 over L energy, the variance, but the envelope takes very low values very frequently. So the receiver suffers from what is called fading. But on the other hand, if you have independent copies of the symbol xk of a given symbol, this is like having independent copies because we're all adding them up coherently. If one of them fades, the other need not fade. There is inherent protection given by the channel, or in this case, some kind of a transmission and receiver method. Okay, the diversity order for this system is, diversity order is equal to L. Well, we are saying it L here because we assume them to have, all of them to have equal variance. Okay, this is an hypothetical channel we constructed, but nevertheless we'll keep it that. Yeah.
What is diversity order?
See, usually diversity order is something that is defined in a slightly different way. Let us say you send, let us say the channel has single one tap, H0, okay? And you transmit the signal, and the receiver sees an SNR of 1 plus H0 square by N0. Okay? And if you calculate the probability of error, that is the mutual information. Let's say for the uncoded system, if you calculate the probability of error, for BPSK transmission, the probability of error, the beta average probability of error can be expressed as and maybe a factor 2 is here, for it is binary. This is the probability of error associated with the match filter bound receiver. There exists a hypothetical receiver that gives you a probability of error given by this expression. Okay? Now, the diversity order can be defined in two ways. In textbooks, what they do is they carry out this expectation with respect to all the random variables. Right? You calculate the average probability of error averaged over different fading channel realizations. So this average is carried out over a long time, let us say. You run this link a long time and you calculate the averages. It can be shown that the probability of error decays as 1 over let's say define some SNR term sigma x square by n naught rise to L, and there is a constant k. We don't have time to derive this, but if you carry out this expectation, the probability of error is some constant k divided by sigma x square by n naught, which is the SNR of the channel without fading, rise to L. That exponent L is called the diversity order. That exponent L is called the diversity order. Whereas in our case, we define the number of terms in the summation as the diversity order. Both mean one and the same because we consider a channel model where all the taps have equal average power. But you may argue that, let us say one tap has very low power, average power, and the other has higher. In that case, the notion of diversity order is it's a little more complicated. But in any case, just take this particular simplified model. That's good enough for the time being. Okay? So, a fading channel creates a loss at the receiver. Why is there a loss? Well, look at this. If L equal to 1, look at the probability of error. 1 over SNR. In a log scale, the slope is 1. Okay, in a log scale, the slope is 1 or rather minus 1. Okay. As L increases, the probability of error decreases quite a bit, right? At least you need L equal to 2 so that you drive down the error rate. So if you have to plot, let me erase. Anyway, you'll do a simulation this week. You'll see the effects of fading. For L equal to L equal to 1, the bit error rate on a semi-log scale will be a straight line, right? Right? When you take the logarithm, it will be straight line. The slope is 1. If you have L equal to 2, diversity order 2, the bit error rate decreases and the slope of the error rate curve is 2. If L equal to 4, so this is called the diversity gain because the bit error rate is decreasing. So for a given bit error rate, if you take a match filter bound or reducible case, this is the loss you get because of fading. Or compared to here, this is the gain you get by increasing the diversity order. So now the question is, how do you either increase or decrease the diversity order? What is the control you have? Well, the channel is not under our control, right? In a broadband wireless channel, typically the number of taps is very large. In 20 megahertz, you will see 20 taps. Okay? So the channel inherently has plenty of multipath diversity. It is up to you how to exploit it. In a broadband channel, there is plenty of inherent diversity. So if you design a transmission and reception or an encoder and decoder cleverly, if you can tap into this diversity that is already available in the channel, you can get to close to the AWGN case, that is no fading scenario. You can with 1 or 2 dB penalty. It's possible. Because the channel has plenty of diversity. In the limit where L is very large, what happens to this metric? If L tends to infinity, what happens to this SNR match filter bound? Any idea? the limit where L tends to infinity, do you know what this tends to? Use center limit theorem. Each tap has variance of 1 over L. You have L taps, L tends to infinity. What happens to this? Yeah, use center limit theorem. This goes to 1. So sigma x square by n naught. In a broadband channel with plenty of multipath delay spread, if you design the encoder and decoder properly, this is the limit for your receiver. And you may say, oh, well, can you have infinite number of taps? Well, a number as close to as 5 or 10 acts like, gives you an effect close to infinity. You know that, central limit theorem, after you sum up 5 or 6 random numbers, random variables, you get central limit theorem effect kicks in. So if you have 5 or 6 independent fading taps with approximately equal average power, you will get this effect. So a broadband channel inherently has a lot of multipath delay. Then you may say, well, what about narrowband channels like GSM? Okay. So what is broadband? What is narrowband? Well, it is the bandwidth that dictates whether it is broadband or narrowband. GSM, let's take even a older generation system. There is what is called IS-54 in US. It's called US TDMA. The bandwidth was 30 kilohertz. Okay, US TDMA. The first digital cellular, well, it's not the first, I think. Actually, it's the first American digital cellular standard, IS-54. It was not used for a long time. I think it was used for about 5 years. The bandwidth was 30 kilohertz. Okay. In 30 kilohertz channel, if you resolve these taps in a 30 kilohertz channel, the TS will be very long and you will not observe so many taps. You will end up with a single equivalent tap. In 30 kilohertz channel, the receiver observes a single tap. So all these taps sort of combine and merge into single effective fading tap. It's called a flat fading channel. It's almost like line of sight with some fading. I mean, equivalent line of sight with fading. It's not really line of sight, there is scattering around you. So a 30 kilohertz channel is a flat fading channel. And then you may say, oh, the channel doesn't have much of multipath to exploit. Well, yes, there is not much multipath to exploit. So what you do in that case is that you use multiple antennas at the receiver and separate these antennas with sufficient spacing, several wavelengths apart, and hope that there is this scattering, and combine the outputs of these antennas and you get antenna diversity. Well, it will still give you an effect like this, where this L is no longer the channel, the multipath taps, it is the number of antennas. If 2, you have 0 and 1, 2 antennas, and then you call, well, I have the second order diversity using 2 receive antennas. If I have 4 receive antennas, I have fourth order diversity, because the channel is giving me nearly flat channel. I mean, nearly flat impulse, single tap with flat response frequency domain.
But in GSM mobile phones, the length between the two antennas is quite large. So
In the phone, you mean?
Yeah.
Usually, you need half a wavelength separation between the antennas. If at all there is risk scattering around the if it is a risk scattering environment, then the fading that you see on one antenna is uncorrelated with the fading you see on the other antenna. So you need a few centimeters. You need that. Well, it depends on the carrier frequency, right? If it is 800 megahertz, what is the spacing required? It's on the order of 30 centimeters.
0.3 meters.
30 centimeters. Yeah, that's quite large. Yeah, that is. You need an iPad-like device to give you 30 centimeters. So that's why GSM phones don't have 2 antennas. That's a simple reason. In that case, what you could do is you place these antennas at the transmitter. And base stations can place them sufficiently far apart and get what is called transmit diversity effect, but you have to transmit the signals with some sort of special encoding, which is called space-time coding or MIMO, because you can't just transmit the same information on both antennas. That won't give you transmit diversity. You have to do something different. What you transmit on first antenna at the base station and what you send on second antenna, maybe it should be delayed or phase shifted, something like that. Okay, we'll discuss that in the MIMO section. Okay, we'll discuss transmit diversity. So we're kind of sort of jumping ahead here. We're talking about diversity, but not antenna diversity here or MIMO, but rather we're talking about the diversity from the point of view of what the channel offers, what is already there in the channel. If there is plenty of diversity, exploit it. Narrowband systems need multiple antennas to give you this extra diversity because the channel didn't give you enough diversity because it was a narrowband system. Whereas broadband systems like OFDM, very high bandwidths, you can resolve the multipath taps into fine resolutions, and then you get plenty of multipath components. And if you design the transmitter and receiver in a clever way, you can exploit this diversity. Well, we haven't taught you yet how to exploit this diversity. This is just a bound we're talking about. We're just talking about a bound, the best that you can probably achieve, and you probably won't get to reach that bound so easily. Okay, is it clear, the notion of diversity now? Yeah. So I think the bottom line is you have to understand the wireless channel. Right? The whole magic is in the wireless channel. How do you get to this? How many taps do you have as a function of bandwidth? If you have 30 kilohertz, how many taps do you have? If you have 5 megahertz, how many taps do you have? For that, you have to go back. I think 1 or 2 lectures back, we talked about wireless channel, frequency domain, so on and so forth. That is something you have to understand. The RMS delay spread, coherence bandwidth, coherence time. These are the concepts that have to really sink in. If you understand them well, then you understand the notion of diversity, and then we'll talk about designing a link. Right? It's really important to understand the physical wireless channel before you jump into OFDM and other things.
So, as you said, we can control the diversity by using, by putting more than one antennas.
Right.
The receiver and the transmitter.
Right.
So when say we have a frequency band in such a way that the TS, both the H1, H0, H1 come into picture rather than having a single big.
When you mean lot of multipath.
Yes.
In that case, if the channel, if the frequency, if the propagation channel already gives you a lot of multipath diversity, there is no need for additional antennas to get per se diversity. There is no need.
And
there is no need for antennas. But these antennas can be cleverly used for other purposes, what is called spatial multiplexing, MIMO in a more general context to increase the data rate. That we'll talk about in the next half of the course. You can still use antennas, but for a different purpose.
So this kind of diversity we don't have control on.
Unfortunately, this kind of diversity you don't have control because this depends totally on the environment, urban, suburban, rural, and so on and so forth. But generally, when the bandwidth is so high, 20 megahertz, you can safely assume that there is enough multipath that you're not diversity starved. There is enough diversity for the link. Okay. There is really no reason why you should put multiple antennas and give transmit diversity or receive diversity when the channel has so much diversity built in. But on rare occasions, you may see a channel where there is only 1 or 2 taps. Well, 2 taps is good, secondary diversity, that's enough. But if you only have 1 equivalent tap, then you need diversity. But that occurs very rarely in a broadband system. Okay, there is no real need to give antenna diversity in a broadband system. This is sort of a very controversial statement because most systems like 4G, they do have transmit diversity as a feature, but that feature is probably not, going to give you a lot of benefit. Okay, that I can tell you with a lot of confidence. Okay, so let's find a way of tapping into this rich, the diversity offered by the rich scattering channel. How do you tap this? How do you exploit it? Okay. In OFDM, the way of exploiting this diversity is through channel coding. Well, that you can see from this expression. When you're talking about, a metric like mutual information, sum of mutual information over all the end tones, and the upper bound says that there is a lot of diversity to be gained. And we don't know how close you are to the upper bound, but you can be depending on the channel code rate you use. As long as you design a channel code properly, it is possible to exploit the transmit diversity, the multipath diversity gain. Okay. In other words, if you have a capacity achieving code that gives you this much capacity, then the problem is solved. Because each tone has gone through HK and you have comfortably benefited from multipath diversity. Okay? It's not so obvious to see it from this expression, but intuitively that's what it means. If you have designed a code to achieve this mutual information, there exists a code to achieve so much rate with zero error probability. That means you have beaten the fading. Right? If you have achieved zero error probability using certain code, that means fading has not caused you much damage, because we know that there is plenty of diversity to be exploited. Okay?
So, what channel capacity we assume for that?
This is the mutual information of the capacity of the channel. This is the capacity. So if you hit this, you're good, because there is plenty of diversity, and of course, as long as L is a very large number. If L is 1 or 2, then this capacity itself fluctuates a lot because of this HK, which is not a sum of, which is not contributed by infinite number of taps. If you have a single tap channel, this capacity fluctuates. It's a random variable with a given mean and a very high variance. If L tends to infinity, this sort of reaches a constant value, because we said that the match filter bound itself reaches the constant values. So this should also reach a constant value. You can take the expected value of this, and that will give you a constant value, and the variance you can show that it goes to 0 as when L tends to infinity, or if it is a large number. Okay? If L is not a large number, then you have to define what is called outage probability. Okay? If L is not a very large number, you have to define what is called an outage probability. Okay, let me write down the definition for an outage probability. Okay. You choose a rate R at the transmitter. The transmitter chooses a rate R and transmits information. Does it make sense? You choose a rate R. And the channel has a mutual information of so much for that particular realization of the channel. If R is greater than IN, what happens? Well, you can't decode the information reliably and an outage occurs. You send a sequence, long frame, which is coded sequence, a frame at a rate R, and it so turns out that this IN, which is this mutual information, is less than the R. So you have transmit a rate higher than what the capacity of the channel. So an outage occurs. So this is the probability of outage. So I can write this as probability of IN less than R is the outage probability. Okay. Whenever L takes small values 1, 2, 3, this outage probability has a lot of significance. From information theory point of view, it has a lot of significance. What is the significance? It turns out that you construct a code with rate R, and the average frame error rate that you get with this code is something like this. This is the frame error rate for a code with rate R, and this is the SNR. This is the frame error rate, and the outage probability is a lower bound on the frame error rate. Okay, this comes from information theory. You can just take it as a design rule. Okay, the outage probability turns out to be a lower bound on the frame error rate, and they have the same slope. They have the same slope. You know what is slope? Okay, the frame error rate has an expression like this. Of course, this is uncoded. In coded case also, the frame error rate will have an expression, some constant divided by SNR raised to some power L. This can be written as some K0 divided by SNR raised to some power L, and both of them have the same slope, and that slope is called the diversity order. Okay, so we're talking about two different things here. At first we said that there is a channel with infinite length, and then this reaches a constant value, then you can only transmit it that rate, right? There are no outages in the system because there is no fading. Sort of fading disappear. But if L is finite, 2, 3, 4, 5, but of course beyond 5 again this curve becomes almost like a vertical line. Okay. For L equal to 1, 2, 3, 4, you can define what is called probability of In less than R. So R is a fixed quantity, then this is the CDF of the random variable In. Is it right? If you take In as a random variable, this is the CDF of the random variable In. So, and the outage probability acts as a lower bound on the frame error rate. Okay? And the slope of the outage probability curve is also called diversity order. Okay? This is sort of ambiguous because it comes from information theory, and we didn't show how to arrive at this result. But I think what we will do now is we jump to a very practical encoder and decoder. Very practical encoder decoder. What would you take? We'll take something like a convolutional code, pass it through, take a convolutional code, put it through OFDM transmission, receive it, and what is the diversity order you will get? We can in fact compute it analytically using a sort of a rule of thumb, and we will simulate it and measure and verify it. I think we can take comfort in that instead of looking at this way of. Okay. So what we will now do is we'll take what is called bit interleaved coded modulation. Okay. Okay. Yeah.
Will you please once again tell how we implement this outage probability while designing this code with radar?
Okay. It needs a bit of a thinking. Let's define outage probability. This is the probability. This is P out. That is equal to probability of In less than R. You choose the rate R. Okay. Unfortunately, In is a function of the channel, and the channel changes from time to time. Right? But the variation is, well, channel changes from one time epoch to another. Okay, but you fix this rate R. Every time the mutual information falls below R, an outage occurs. and you want to calculate this rate, right? How many times it happens? That is the probability, right, of occurrence of this event. Okay, you want to calculate this probability of occurrence of R greater than IN, and IN is okay. But what is really important is the underlying channel H of L and how many taps are there. Okay. Okay. If L takes values on the order of 1, 2, 3, let's focus on them. Do you agree that IN is a random variable, right? Because these are the distribution, these are the distribution. Well, it's a random variable, right? If IN is a random variable, you can calculate the probability of IN less than R. Can you? Okay, because you know the PDF and CDF of IN, you can calculate it. By some means, you will calculate the PDF and CDF of IN, and you can calculate this probability. So you fix a rate R, okay, and you fix a value N naught. You fix a value N naught. Okay, so I will take 1 over N naught, sigma x square by N naught. I will take one point here. For that point, I can calculate this probability. And now I take another N naught. This is P out. Okay. This P out is an outage probability. It doesn't even depend on the length of the frame, particular modulation, particular coding. It doesn't depend on anything else. It depends on the rate R. What is the units for R? Bits per symbol, let's say, channel use. And R is typically chosen in the order of 1, 2, 3, whatever it is, 0.5, 1, 2, 3. 1 is like sending 1 bit, 2 is sending 2 bits per channel use. Okay? But you have fixed R, right? You're not going to change it with SNR. You have fixed R, you're not going to change it. So the transmitter has agreed on a given rate R independent of the what receiver sees. Sometimes you will see a mutual information either higher than R, or sometimes it is lower than R. But what you would do is, as a transmitter, you will be greedy and you will choose R high enough. That's what would happen, right? If you choose it too low, then the throughput of the system goes down. So you usually tend to choose it high enough. When you choose it high enough, then outages occur. Right? The receiver experiences errors. This is totally an information theoretic measure. It turns out that this is a lower bound on the actual frame error rate that you would get if you design a code with rate R. If you design a modulation and coding scheme with rate R, like a convolution code followed by maybe, let's say, BPSK or QPSK, it gives a total rate R, right? Right? R is the total rate R is the channel code rate multiplied by log m base 2. Okay? R in a practical system, R would be small r, which is the channel code rate if you use a binary code, turbo code, or convolution code, and log m base 2. Those are the number of bits per symbol. Okay. So this is, you can design a code like a convolution code or a turbo code, and it has a frame error rate, right? You can measure the frame error rate. You can choose a long enough frame and measure the frame error rate. In information theory, you have to, capacity is achieved when the frame size goes to infinity. Okay, so you have to choose very large frames. Okay, anyway, so you choose long enough frames. Frame is a sequence of bits. And you get a frame error rate. It turns out that this outage property is a lower bound on the frame error rate, and there may be a small gap, it's a bound. And they have, both of them have the same slope, and the slope is called diversity order. Okay? This is if the receiver does not give any feedback to the transmitter. Let's look at another scenario. The receiver continually measures IN. Let's look at another scenario. This is case 1. Case 2, receiver measures IN at that given time and feeds it back to the transmitter, and transmits at the rate IN. Is there an outage? Well, slightly below that. There is no outage. So receiver will never see outages or errors because receiver is communicating to the transmitter IN and transmitter transmits at the rate IN. This is called adaptive modulation and coding basically. You tell the mutual information to the transmitter and transmitter constructs a modulation and code rate so that a receiver will decode it successfully. Right? This is with feedback. It's called adaptive modulation and coding. So IN is fed back to the transmitter and no outage occurs. But the transmitted rate has become not a constant but a random variable. Is that right? In case 2, case 1, outages occur. But the transmitted rate is fixed, R. It's fixed at R. Let's look at case 2. Case 2 is the receiver measures IN and quickly transmit to the transmitter. Transmitter exactly knows IN, and we hope the channel is varying very, very slowly, and transmits at a rate IN or slightly below that. Then no outages. But then what is the transmitted rate? It's IN. IN is a random variable whose variations depend on the variations of the channel. Therefore, your transmitted rate changes as a function of the changes in the channel. So the transmitted rate in case 2, let me write down. Case 2 with feedback receiver reports IN to the transmitter. Transmitter transmits at a rate slightly below IN. Well, what is that transmitted rate? IN, which is changing. So your rate is IN, that is equal to log of base 2 1 plus hk square by n naught sigma x square summation over k equal to 0 to n minus 1. Okay? Now you can talk about average transmitted rate and the variance of the transmitted rate. Okay? And if the channel length is very small, if you have a, let us say L equal to 1, and if you have a flat fading channel, you can see that this rate goes through a lot of fluctuations because this will be flat faded. If the channel length L equal to 1, in fact you can plot from the transmitter point of view SNR defined as sigma x square by n naught, and you can plot expected value of IN, and you can see that for L equal to 1 you get something like this, for L equal to 2 you get something like this, and then for L equal to 10 you get something like this. What is this? Expected value of IN, the capacity in bits per symbol, function of SNR. This is a little different. Capacity versus SNR. For L equal to 1 you see a loss because, but where do you lose this? When you say loss, what has been lost? The transmitted power, a portion of it is lost in the fading channel. But when you have a lot of multipath, you recover some portion of it. And in the limit, you will reach AWGN, capacity versus SNR. Of course, here expected value of IN. So there are different measures that you can use to see how well the system is functioning. One is expected value of IN versus SNR. This doesn't talk about outages. This talks about average rates, and you assume that there is feedback. But if you don't have any feedback, if you agree on a fixed rate R and you live with the outages. The first generation of cellular standards like GSM and TDMA, they didn't have feedback from the receiver. They agree on a given modulation and code rate and hope that it goes through. But in the second generation of cellular standards like 2.5G, GPRS and Edge, they introduced feedback from the receiver to the transmitter. The feedback is in the form of either mutual information or some effective SNR. Mutual information is there is one-to-one mapping to some effective SNR, and based on that you can control the modulation size and the code rate to come up with a single rate R, which is a product of code rate and log m base 2 modulation size. And with that, at different points in the cell site, your SNR varies, and when you're closer to the base station, you pump a lot of bits through. When you're farther from the base station, less bits go through, or if your interference is high, you reduce. So you kind of adapt to the SNR. But of course, this feedback requires very quick feedback through an uplink channel, because wireless things are very unpredictable. Channel can change pretty rapidly. Okay, so this is kind of a high-level overview of what happens in a link. You can have either feedback or not have feedback. When you don't have feedback, what you have is outages, and you talk about a single link with outage probability and things like that. When you have feedback, no outages, I mean theoretically speaking, and the transmitted rate varies, then you need adaptive modulation and coding. In the next lecture, we'll talk about a specific modulation and coding scheme that can achieve either the outage probability or the outage probability in the case of fixed rate or zero outages when you have feedback. Something practical that will achieve the optimum performance. Okay, so regarding the simulation assignment, you should now introduce a cyclic prefix with this. Well, I erased it. L-tap channel, where L is 2, 3, 4, any number you specify it, and variance of each tap is 1 over L, and you should be able to demodulate with BPSK. Okay, that is assignment. After we introduce the convolutional code, I'll give you a piece of encoder and decoder. You integrate it into your simulation chain. Right? That should be okay, right? I'll be sitting downstairs, so you come and see me if you have any doubts on the assignment. So you can bring your laptop, sit there. Read this material on wireless channel modeling. Okay? It's important to know what it is. Yeah. First simulation, I think you should give, I think day after tomorrow. And second simulation.